We're going to look at the ionic bonds that produce an ionic compound, and we're going to use electronegativity. So let's take a look at hydrogen and fluorine as an example. First thing we want to know is the nuclear symbols. So we know that hydrogen has one proton, atomic number is 1. Therefore, since there's no charge here, it also has one electron because we know it's neutral. This indicates the mass, which is protons plus neutrons, so there's no neutrons here. Fluorine is 9 and 19. So we have 9 protons, therefore 9 electrons because it's neutral. The mass is 19, so you subtract 9 from that, you get 10 neutrons. Both of these atoms are electrically neutral, but they're not stable. We're going to draw the electron configuration for both. Hydrogen's pretty simple. It just has a 1s electron standing out there all by itself. So we know that hydrogen usually acts like a metal, meaning it will lose that electron and become a positive cation. But it can also be a hydride, which means it could gain an electron. So it acts like a non-metal and becomes an anion. But we're going to focus on hydrogen being a metal. Usually they place it in group 1. Fluorine, on the other hand, is a halogen, group 7. Since it's in group 7, it wants to gain one more electron to make that octet rule and be stable. But let's go ahead and draw this. We have 9 protons, therefore 9 electrons. We draw the first one. First energy level has one sublevel, S, and then we're done. So we go to the second energy level. The second energy level, which is the valence in this case, has 2 sublevels, the S and the P, so 2S and 2P. Notice P has 3 orbitals. I put it in black because this is our valence and it'll stand out. We have 9 electrons, 2 went here, so we have 7 left. So 2 more go here, and then we count them. 1, 2, 3, that's 5 more. We have 2 left. Notice Hund's rule. In the same sublevel, you have to split up the electrons because they repel. There's our valence. This is an unpaired orbital. That's where fluorine wants its electron. There's a pretty easy solution. This electron could go there. First we need to see if that's what's going to happen. And we do that by looking at electronegativity difference. Hydrogen has an electronegativity of 2.2. Fluorine has an electronegativity of 4.0. Now it does not matter how many atoms you have of each. We just simply find the difference between these two, which is subtracting. 4 minus 2.2 is an electronegativity difference of 1.8. We said that 1.7 is our cutoff between ionic, which is above 1.7, and covalent molecules, which are below 1.7. That this indeed will be an ionic bond. Therefore, this electron is going to transfer over. So watch what happens. Since this lost an electron, it becomes positively charged. Since this gained an electron, it becomes negatively charged. It's that positive to negative which becomes what's called an electrostatic attraction, making it the bond. We can look at it another way using electron dot. Look at hydrogen. It had 1 electron here in its valence, therefore 1 dot. Fluorine has 7 electrons in its valence. And I'm going to use X's just so you can see the difference. 1, 2, use Hund's rule, 3, 4, 5, and then put the other 2 somewhere else. Fluorine desperately wants an electron right there. It can get that electron from hydrogen. This electron will end up over there. The electron transfers. As soon as it leaves hydrogen, hydrogen becomes +1. As soon as fluorine gets it, it becomes -1. And there's the electrostatic attraction. And to write the formula, we would write it as H plus F minus. So 2 things are required for any bond. Number 1, it needs to be electrically neutral. +1 minus 1 is equal to a net charge of 0. The second condition is that both atoms, or all the atoms involved, must have complete valence. This has a complete valence, it has nothing. And this has complete valence, it has 8 in its outer shell.